So let's talk about what we know so far with our series, which is not much. We only know one thing. We know that if the limit as n approaches infinity of a sub n does not equal 0, then the summation from 1 to infinity of a sub n diverges. And that is all the nth term test says. So if you can apply this, this is like our quickie test. This is a quick test, or a quickie, our quickie test. So if that happens, you say diverges. Now, it doesn't say anything else. That's it. And then I said in our video, you cannot argue for convergence with the nth term test. What I'm going to add today is a couple of tests to tell convergence. And that's called the geometric series test and the telescopic series. Now, we are only going to be doing this if the nth term test does not apply. It's really nice when the nth term test does apply because it's quick to say divergent. You answered it and you're done. It was a series, and this is the limit as n approaches infinity. The horizontal asymptote to this is 1/3. Remember that from pre-cal, if you have a polynomial over a polynomial and the degrees match, then it's just the ratio of the coefficients. The horizontal asymptote is 1/3. Hey, that does not equal 0. So by the nth term test, this series diverges. So that should have been your answer to number 1. All right, so let's go to number 2. You were only supposed to tell me if the nth term test applied or not. And if not, you were supposed to see if you could figure out what they converge to. But that was just a little gravy, a little bonus to see if you could do that. Number 2, if you know the graph of arctan, it does something like this. It's got horizontal asymptotes at positive pi over 2 to the right and negative pi over 2 to the left. So the limit as n approaches infinity of arctan of n is pi over 2, which does not equal 0. Therefore, by the nth term test, this diverges. All right, number 3. This is the first one that you should have gotten. We can rewrite this as e over 3 to the n power. And e is a number less than 3. And this is our first example of a geometric series. By the way, the limit as n goes to infinity of a fraction less than 1 to the n power is 0. This means we cannot use the nth term test. So your answer to this should have been, I can't use the nth term test. It does not apply here. Well, I'm going to show you how to do this one now. This is a geometric series because you've got a ratio or a fraction to the nth power. There might be a number out here in front of it, but you have a ratio to the nth power. And if you ever have this, and here we're starting from, I guess we're starting from 1 to infinity. This will always be the first term divided by 1 minus r. I guess the way I have this written, I need to have that starting 0 to infinity. So the first term would just be a sub 1. But it doesn't matter. If you have a geometric series, that's a fraction to the nth power, going to infinity, this will converge to this sum if and only if that common ratio is in between negative 1 and 1. And it's the first term divided by 1 minus r. This is what it converges to. So what we can say is, if you have a geometric series, a fraction to the nth power, it will converge if the common ratio or the fractions in between negative 1 and 1. And not only that, you know what it converges to. So here we can actually answer both questions that this chapter is devoted to. Does a series converge? And if it does converge, can you tell what it converges to? So this one, I don't know if you guys played around with this on your calculator. This one actually converges, and it converges to a specific number. So what we want to figure out is, what is the first term? So we're going to go to the series. The series starts with 1. So we're going to plug 1 in for n. And so the first term is e to the first over 3 to the first. That's the first term. Now, the common ratio is the fraction, which is just e over 3. So this converges, and it converges to the first term, e over 3, divided by 1 minus e over 3. And that is what that would actually add up to. We'll see another example of this in just a second. Okay, number 4, the limit as n approaches infinity of 1 over 10n plus 7. 10, oh, we're getting the eraser out for that one. That's too much of a mistake. Try again. Love that eraser. That's fun to do. It's way funner than it looks. 10n plus 7. From pre-cal, you learned that if you have a bottom-heavy fraction, this goes to 0. Now, so you should have said the nth term test does not apply here. And we're going to keep a big question mark on this one because we haven't learned how to deal with this one yet. That's coming in a day or so. Now, this next one, if you were to multiply this out, you get the limit as n approaches infinity of 1 over n squared plus n. And this is also a bottom-heavy fraction. This goes to 0. And so you should have said nth term test does not apply, but on this one I'm going to show you we can actually figure out whether it converges and what it converges to. This is a telescopic series. It's like a telescope, and I'm going to show you why it's like a telescope. If we use partial fractions, we can separate this into 1 over n minus 1 over n plus 1. You can check that with partial fractions, and so I've got this summation from 1 to infinity. Let's take a look at this expanded form and see what happens. If we plug in 1 for n, I'm going to get 1 over 1 minus 1 half. Then, if we plug in 2 for n, we get 1 over 2 minus 1 over 3. Then if we plug in 3 for n, we're going to get 1/3 minus 1/4. And then if we plug in 4 for n, we get 1/4 minus 1/5. And I'm going to go one more, plus 1/5 minus 1/6. And it keeps going like this, but I want you to see what happens. Just like a telescope, you know, like pirates use, I'm a pirate. You know, the telescope will actually collapse on itself. This series collapses on itself because watch what happens. This negative 1/2 cancels with that 1/2. This negative 1/3 cancels with that positive 1/3. Negative 1/4 cancels, and you can see by this pattern that everything else after this first term cancels. And so what we get is a telescopic series because everything after this collapses, and it collapses down to have an answer of 1. So I get a convergent series, and on top of that it converges to 1. It's called a telescopic series. Okay, let's take a look at another one. This is a geometric series. It's just sort of a geometric series in disguise. So let me show you how to deal with this one. The 3 to the n minus 2 can be rewritten as 3 to the n times 3 to the negative 2. Remember your properties of exponents. And on the bottom, I can call that 2 to the n. Now, 3 to the negative 2 is the same thing as 1 over 3 squared. So I can drop the 3 squared down here. And a property of pretty much everything we deal with is this is a constant. This doesn't have an n on it. So I can take that all the way out in front of our series. And I can simplify this down to a geometric series. This is a fraction to a power. Now in this instance, my common ratio, or the thing that's being raised to a power, is 3/2, which is bigger than 1. A geometric series where you have a fraction being raised to a power that's bigger than 1, this is divergent. So this gets bigger and bigger and bigger. Now you might have argued an nth term test here, because the limit as n goes to infinity of something bigger than 1 to the nth power. This grows to infinity. But this is a divergent geometric series. You could have also said diverges by the nth term test. Okay, let's take a look at this next one. And let's rearrange this. This is 3 to the n plus 1 over. I'm going to rewrite the bottom as 3 to the n times 3 to the first. And I have my little summation here. I'm going to take this 3 to the first all the way out in front, and I've got a summation of 3 to the n plus 1 over 3 to the n. Now we can also separate this into two series. So I'm going to put a little bracket here. I don't know if that's needed, but so my first series can be the 3 to the n over 3 to the n. And then the next series is 1 over 3, and that's all to the n power. Remember, 1 to the n power is just n. It's just 1. Oh goodness! Back to the eraser. Okay. 1 over 3 to the n is the same thing as 1/3 to the n. That's what I'm saying here. Okay, so what I have is, wow, my pen's really being messy here. This is a geometric series on this side, and it is a convergent geometric series because the common ratio is 1/3, which is less than 1. So this converges, and on top of that, this series converges to the first term. Now the first term is plug in 1 for n, you get 1/3. So it converges to the first term divided by 1 minus the common ratio, which is 1/3 divided by 2/3, which is, well, it's 1/2. So this adds up to 1/2. Equals 1/2. Now, however, what about this other thingy here? This is also a geometric series that can be rewritten as 3 over 3 to the n power. And remember what we said about geometric series. Our r has to be between -1 and 1. It can't be equal to 1. See, this series right here would be, if you simplify this would be like 1 plus 1 plus 1 plus 1 plus 1, which obviously grows to infinity. So what I have here is 1/3 times an infinite series plus 1/2. And unfortunately, infinity plus 1/2 is still infinity, and even if you divide infinity by 3, we still get infinity, so I get a divergent series here. Alright, this one we're going to deal with number 9 later. This was divergent because of the nth term test, but it's also because the factorial is much more powerful than any exponential. Factorials will outgrow exponentials, so that diverges to infinity, and actually pretty quickly. And we're saving number 10 for later too. I want to do one more interesting example, and that is like the number 0.99999 repeating, ... This is a infinite geometric series. This is 9/10 plus 9/100 plus 9/1000 plus ... There's 9/10 plus 9/100 plus 9/1000, blah, blah, blah. This can be rewritten as 9 over 10 plus 9 over 10 squared plus 9 over 10 cubed plus 9 over 10 to the 4th, blah, blah, blah. So I can factor the 9's out, and I have this as 9 times 1/10 to the n power. Summation n going from 1 to infinity. Plug in 1 for n, you get 1/10 times 9. There it is. Plug in 2 for n, that's the second term. This is a geometric series, and your common ratio is 1/10, which obviously is less than 1, so this is a convergent geometric series. We also can tell what it converges to. The way you do that is you figure out the first term and divide that by 1 minus the common ratio. So what is the first term here? Well, I've got it written out here, it's 9/10, but also you can plug in 1 for n, and you can see the first term is 9/10. So this sums to first term 9/10 divided by 1 minus the common ratio. So what do we get here? We get 9/10 divided by 9/10, and of course we know anything divided by itself is 1, and we've just proven that 0.9 repeating equals 1.